So, without further ado, this is a talk that is presented by Dr. Dominic Hames. He's a principal engineer at HR Wallingford. He's also a visiting lecturer at the universities of Brunel, East London, and IHE Delft in the Netherlands. Dominic has over 30 years of experience in flood and coastal defence work, and most recently has won the ICE Halco Prize for the last 2 years. So, without further ado, I hope you enjoy the talk by Dominic. A reminder just to put technical issues in the chat, and any questions to do with Dominic's talk, put them in the Q&A, and we'll come back to those towards the end. But without further ado, I'll leave it over to you, Dominic.
Okay, thanks very much, Sam. Okay, so that's the title of the talk. Just a couple of sort of additional housekeeping things. I have had internet connection issues over the last month or so. If you do lose me, I'll probably be back within about a minute or two. I have a small yappy dog, and if people come to the door, the phone will ring, at which point the dog will yap. But we'll just deal with that as it comes along. It's half term where I live at the moment, but fortunately my children aren't around. Otherwise, they would probably disturb me as well. Okay, so I'm keeping the talk fairly low key. So there's no equations, there's no detailed explanation of how things work, etc. And I split up into two parts. So first of all, looking at the prediction extreme, just the general concept. Then we'll look at why do extreme predictions change. And then I'm going to look at how they change in the future, just basically in terms of climate change. And I've looked at that, I call that part one. I'm then going to go to the second part of the talk, say what are the data quality issues with sea level data? How do these potentially change extreme predictions? And then I'm revisiting the concept of how extremes are likely to change in the future in a slightly different way from what we traditionally think of in terms of climate change. Now, in terms of doing extreme, if we're looking at extremes, how we predict them, etc., the first thing we've got to do is get our data. So if we go back back to even the 16th or the 17th century, for example, when we first started collecting sea level data, or the French did, this was traditionally done off sort of tide boards, off the entrance to docks or harbours. So there'd typically be possibly two sets of these, two on either side of lock gates, often inside and outside the lock gates. And the one I show here is at Silloth in Cumbria. So this is a metric tide gauge, the first in the UK. And as I said, you just literally at high tide, you just read it off the tide board. I have seen records where sort of Victorian times where these have been recorded every minute. So clearly somebody stood there all day, 24 hours a day, sort of recording the tide off a tide board every minute. Move forward a bit, okay, so a little bit more advanced. So get a bit more advanced, we have this sort of what we call a stilling well, a sort of metal tube about a metre in diameter, which go down into the water surface. Little holes at the bottom to let the tide in, but also to make sure that it damped out the waves, so the water level rose as the tide rose. They'd have a little ball in there attached to a wire or string or whatever, and as the tide went up and down, you'd have this would be recorded on a tide gauge. This is a Monroe tide gauge at Newlyn in Cornwall, and this drum with a little bit of paper on would rotate once every 24 hours, and the pen would go up and down with the tide, and they would trace out the tide on a paper chart. So this would be about a week's record. Move forward a bit further when we get to the more sort of electronic age. So the most sort of common tide gauge used now are sort of pressure gauges, and so this is a bubbler gauge on Green Island in New Zealand, and simply what it does, it sort of blows. It's called a bubbler gauge. It sort of blows bubbles, and the pressure required to blow the bubbles out to the bottom of the tube gives you a measure of the pressure. So the pressure, and you can relate and then from the pressure you can work out the depth of the water. In more modern gauges, we sort of have the acoustic or radar gauge, which sends down a pulse down to the water surface, so you can get the water level off those gauges. And in terms of what they record, they typically record them in 4 different ways. So we have in digital regions these days are typically every 15 minutes. So the National Tide Gauge Network, the tides are recorded every 15 minutes. EA Tide Gauge is every 15 minutes. But other organisations like ABP or sort of other people that record sea levels can record anything between about 1 and 15 minutes. So you get some records around the UK, for example, or elsewhere in the world recorded every minute, but typically every 15 minutes. We go back to the sort of dawn of the digital age, about early 90s. They were typically recorded, if they were recorded On a time series, they typically recorded hourly. So, for example, the National Tyre Gauge Network up until about 92 was recorded hourly. And then also prior to the digital age, they often recorded the high waters or sometimes the low waters. So they recorded the high waters. Sorry, I just got stirred then. So you'd have high water, but so you just have one record every high tide. We also have annual maxima, so certainly going back to the 20s or even further back, you just have one record recorded per year. Usually there's not a date associated with this, so you'd have the records, but you wouldn't know what date it was. You could probably work it out to an extent. And there's no way of checking that data, but with typically no other records, no paper charts, etc. So in terms of the prediction of the extremes, so they started off. So this is the Immingham and the Humber. So what I've outlined here is the main prediction of extremes at Immingham since the first prediction of extremes in 1981 by somebody called Jerzy Graf at Lancaster University. And the interesting thing to note about this to start off with is that even on the low extremes, the variations. So we have, for example, the 1 in 10-year prediction varies by about 400 mils, which is a significant variation for such a relatively low return period event. We then ask, okay, so why do these predictions change? Why have they changed? Why have they changed historically so much, and how are they likely to change in the future? Okay, so the first reason is the change in methods. Okay, so before the digital age, up until about 1992, essentially all we had was annual maxima, one record per year. So this is so what you find. So one of the problems you find with this is, as we're only looking at one record per year, there'll be certain years where you may not have many records, or you may not have any particularly large water level in that year, but it counts in the analysis. So you have to always include one record per year. There'll be other years where you may have several large, big storm events, several extreme sea levels, but you only count one of those events. And what you find the annual maximum method in terms of sea level predictions certainly is that it often tends to underpredict the low return period events. So, for example, we can see here, for example, from Jerzy Graf's predictions in 1981, a very, very low estimate of the 1 year return period, because that would have occurred in a year when there wasn't any particularly large events. We then move forward to when we sort of switch in between the annual, when we get sort of digital readings coming in, and then finally we get through to where we are now, where we are now. So these are the last three major predictions of extremes at Immingham. We're in the digital age where we can look at sort of time series, and we can look at all high sea level events, regardless of when they occur. Another reason why they change is the distribution of extremes. So this is an extreme sea level prediction on the Humber, okay? And in 2013, 5th of December 2013, we had by far the largest sea level ever recorded at Immingham. And it was about 0.4 meters, and the next highest, which occurred on the 1st of February 1983. And this can have a significant effect on extreme predictions. Every time you get a really big event, you redo your extreme value analysis, it will noticeably change an extreme. Interestingly, we have the 1953 event, the most famous flood event affecting the UK, the last where we had, I think, a region about 300 people died in the UK on the coast, the biggest natural disaster of the 20th century. It's only the 6th largest event since then. So at 1953, it was by far the largest event ever recorded at Immingham. But since then, there's been 5 bigger ones. And the other 3 are 1969, 1978, and 1976. Okay, if we look at the 3 of these events, okay, and so it's to show why predictions change. We have the first prediction in 1981. That was done before the 2nd largest event ever occurred. So unsurprisingly, that is the lower of the 4 that I've shown there. We have the predictions done in 2011. So this is the Environment Agency Coastal Flood Boundaries Report. So if you did a flood risk assessment or planning application after 2011, this would have been the extreme sea level predictions you would expect it to use. And you notice these are a little, and so this is before the 2013 event, and a little bit lower than the predictions done in 2014 and 2018. The predictions done in 2014, which are known as the Interim Humber levels, they were done after the 2013 event. They did exactly the same methodology with exactly the same data set as the 2011 predictions. The only difference was it included a little bit more data, including that 2013 event. And that 2030 event is the reason they are about 200 millimeters higher. And then the current predictions in 2018, which is the replacement coastal flood boundaries. Now, if we look at how predictions changed, so I'm just going to demonstrate how predictions would have changed at Immingham since 1956. So using the same method, a very simple method. So in 1956, if you did an extreme sea level prediction on your 100-year extreme, so this is when you had 1 year of data. So this includes missing data. So there's 1 year of data, even though we have big gaps up to 1956. Your 100-year prediction would be about 5.04. You do it the following year when there was quite a series of large events in 57, not as big as 53, but there was a large sea levels in 1957. It tends to go up a bit. Okay, you then get a period where you don't get any data. So you have predictions in 50, there's data in 58, but then no more data until 62. So it goes down a bit. You then get a period where you don't have any particularly large events, just a normal distribution you'd expect. The predictions tend to go down. We then get 1969 when we have a large sea level, the biggest record at the time. Your predictions go up. We then have another period where we don't have any particularly large events, and your predictions tend to go down and sort of stabilize. And then in 1976 and 1983, we have 3 particularly large events where your prediction extremes go up based on extreme value analysis. We then get a period from 83 until 2013 where we don't get any particularly large events. And as tends to happen with extreme value predictions, they tend to stabilize towards a value, towards the sort of probably the value you probably expect. And then in 2013, we have a massive event in 2013, and your prediction of extremes increase significantly. So this is just to show how predictions change. They tend to reduce in time as you get more data and you don't get any particularly large events. And when you get a particularly large event, when you redo your analysis, they tend to go up and up again. Now, I don't know what the actual answer to the 100-year extreme sea levels is at Immingham, but I suspect if you ask me this question in 50 years' time, it will probably be around about 4.9-ish, 4.95-ish, etc. So this will continue to oscillate, but the more data you get, the oscillations will reduce, and it will probably gradually stabilize sort of constant value. Now, how are they likely to change in the future? I call this part 1. So this is just climate change. So this isn't Immingham. This is Newlyn. I think this is Newlyn down in Cornwall. And here we have predictions in 2020 with 90% confidence bands. There's a 1 in 10,000 year level. There's a 1 in 100-year level. And in 30 years' time, it will look like that with climate change. And in 70 years' time, it will look like that. So 1 in 10,000 year level will be the equivalent of 1 in 25-year level at the end of the century. And what currently occurs every 100 years will occur every year by the end of the century. So that's just based on climate change, but I'm going to revisit this at the end of the talk and look at it a slightly different way.
I'm just going to stop you there, Dominic. Sorry. I'm just recommending you change your snooze on your system reboot to 180 minutes so your computer doesn't decide to shut down on you. So if you change it.
How do I do that? Oh, snooze.
So
okay.
The drop down, yeah, change it to 2 hours, and then snooze.
Okay.
Yeah, there you go.
Okay. So in terms of the data quality issues that you find with sea level data sets, okay, so these are the main ones you tend to find: datum shifts, spikes, datum drifts, time shifts, and I'll also mention other issues that you tend to find with some other issues as well. Now, in terms of what they are, a datum shift is basically where the sea level is recorded to the wrong level. So it can be recorded too high, or it can be recorded too low. And the main cause of that, and when I say the main cause, I'd say 95% certain cause of that, is due to sort of the Tyre gauge being leveled in incorrectly. We also have spikes, and spikes is a single increase, is a sharp increase in the sea level at a particular point, nearly always on a single point, sometimes over 2, but typically over 1 point. And that can be anything from a few centimeters to meters. In terms of the cause of it, not entirely sure, but I think one cause of it is the recording mechanism getting stuck and you suddenly getting released. We also have datum drifts, which is the same as a datum shift, but this is where the datum drifts. Okay, so it's a sort of it changes with time. Again, not entirely sure of all the causes, but one cause would be, for example, we have this in the Moray Firth, where the tire gauge was fixed to a pier, or I think it was a pier, and the pier starts sinking into the mud. That's not the main cause, that's one cause, but I'm not entirely sure why you get datum drifts. Okay. You also get time shifts, where basically the tide is suddenly recorded to the wrong time. Okay, usually over short periods. I've not actually seen a time shift for about 20 years, but they did occur. They did. You know, I used to see them occasionally about 20 years ago. Very, very easy to correct for if they do occur, although you sometimes use a little bit of the record. Now, in terms of actual data, so if you look at actual data, so this is a paper published 2 years ago by Hogarth, Fattel and Simon Williams at NOC in Liverpool. And this looked at the datum shifts, trying to identify data shifts of the Immingham tire gauge on the Humber, the tire gauge which I'm talking about in this talk. And as you can see, when you look at that, so this is part of the National Tire Gauge Network. So this is a tire gauge maintained to the highest standards. And if you look at this, it's probably only between about 1967 and 1980 was probably recording to the right datum level. Okay, and interestingly, in 2013, it was under recording the tide by about 150 mils. So as I said, this is one of only 2 tire gauges I think that's ever been looked at in detail in the UK as a part of the National Tire Gauge Network to look at sort of what the datum shifts are. And you see it's only for a very short period of time does it seem to be recorded to the right datum. The other one is at Workington, and what we have here is the difference between the tide recorded manually off a tie board minus, and so the difference between that and the high tide recorded digitally by the tie gauges. So, and there's three ways they measure tides at Workington. There's a tie board, there's a national tire gauge net, there's a tire gauge part of the National Tire Gauge Network, and there's an EA gauge, which are all separate. And the concept is if somebody records, looks at the reading manually and records it at high tide, most of the time you get it right. Occasionally you transcribe it right. But if you look at the median change over a long period of time, when I use a 3-month moving average here, that will give an indication of how accurately the tire gauges record the high water levels. And to put it simply, what it means is that this orange line here, for example, is the difference between recording the same thing at 2 different ways. That should go along the 0 line. But you can see there are 4 noticeable shifts in the datum. So there's one there, one there, one there, and one there, one there. And this one here, the biggest one here, is about an 18 centimeter time shift. And it was actually, they did go back and re-level the tire gauge around about the end of 2001. And they noticed it was actually over-recording the tire gauge by about 18 centimeters, which is consistent with this line. And these periods of times where there's been a sudden datum shift all coincide with maintenance periods. So they go out, they do some maintenance, and the gauge is clearly re-leveled back incorrectly. The blue line, or from the blue dots, is the difference in the EA tire gauge, and this is an example of a drift. The datum is all over the place. Okay, and again, I don't know why. So this isn't this could be a leveling error, but it's not a leveling error, it's something else. Spikes, this is an example of spikes, a pretty horrendous one. So this is a genuine tire gauge record from Grimsby in 2007. And when you look at that, you may look at that and thinking, oh, that's pretty horrendous. How, that looks completely unusual and unusable. But from experience, I find you can always recover your data, and spikes usually are quite easy to correct for, or to get rid of, or to correct for. So there's usually a genuine tide record. There's usually a genuine tire gauge record in there if you can identify what the spikes are and where they are. This is a time shift, okay, and we can see there's been a time shift there, another one there, another one there, and another one there. And typically these often occur only over about a day or two. So, and I said, I've not seen one of these for about 20 years. Other issues are more interesting. This is a very interesting example of a potential problem with Tyre gauge, which I've only ever observed once. So this is Workington again, and what we have here, we have the Tyre gauges that are recorded in recorded there. So the EA Tyre gauge, the national Tyre gauge, and the manual readings recorded there. And we have the River Derwent here, which discharges into the port, the entrance to the port. Now, if we look at if we plot a graph of the predicted tide at Workington against the EA the surge recorded from the EA surge at Workington, you get what appears to be a linear increase in the surge relative to the tide, which doesn't make sense because the tide is astronomical, the surge is meteorological, and there's no connection between them. Okay. However, if we go back to that figure, of course, what you find is that, oh, sorry, I just lost my voice. Is at low water, at low water, you find that the river is discharged into the port, and so it's predominantly probably fresh water. At high water, when the tide in, is probably predominantly salt water. And so what you find is that what appears to be happening, sorry, just losing my voice. What appears to be happening is that the Tyre gauge has been set up to record fresh water. So up here, when it's salty water, it is overestimating the water level because the water is more dense. And down here, when it's more fresh, it's still overestimating, but it's not overestimating by as much. So it's given a lower surge. So this is an example where I would suggest that the Tyre gauge set has been set up to record fresh water, whereas it's a combination of salty water up here, brackish water down here mainly, and mainly sort of fresh water down here. We also have this data along here, and you may wonder what that is, and that's just simply the fact that the Tyre gauge is only calibrated to record to a certain level, so it doesn't record the very, very low sea levels. Okay. Other problems you get, not with the national Tyre gauge network I've ever observed, is flattening. So this is the Tyre gauge at Spurn Point on the 5th of December 2013, where we had the highest sea level ever recorded at Immingham, and it wasn't calibrated to record to the highest level, so it didn't record the tide. It didn't pick out the peak of the tide. This happens occasionally, but of course it's a bit of a problem if your Tyre gauge is put in there to record the extreme water levels. So the question now you can ask yourself is, how do these potential errors affect extremes? Okay, and I'm only going to look at the concept of a datum shift, which is probably the main problem. What we have here, okay, is a prediction of extremes at Immingham, and what I'm going to do is I'm going to take the distribution of the datum shifts from that graph and apply it randomly to the data at Immingham. So I have a maximum data shift of -150 and a maximum positive data shift of about 50 millimeters. So that's a prediction at the moment. And by applying that data shift randomly to sort of correct the data depending on where those data shifts were, you get a series of different predictions. And what I did, I looked at these, how the datum shifts could affect an analysis, and it suggested that potentially it could make a difference of about about 10 centimeters in this particular case. So what I have here is my estimate of the 100-year sea level, or my best estimate, and the sort of 90% confidence band. So dependent on when the data shift occurred, my 5% of the time, my 100-year prediction could be as low as 5.05. 5% of the time it could be as much as about 5.13 or whatever, but about 50% of the time is around about here. So that datum shift can make a difference, probably of up to about 10 centimeters, about 90% of the time. So the question you then got to ask yourself is, how are these likely to change in the future? Well, I've gone back to this question. So initially I looked at it in climate change, but now I'm looking about how extremes could change in the future. And I'm looking at this in a slightly different way. What we have here is two graphs showing the difference between the extreme sea levels from the coastal flood boundaries done in 2011 and 2018. So this is what you'd base flood risk assessments on planning applications if they went to the Environment Agency. The thing to note here is interesting. This is the 1 in 100-year prediction. We notice around about Silloth, around about the Solway Firth, predictions were out would have changed by almost a metre in some places, and around the Orkneys and around sort of the north the north of Scotland, you find that some predictions have increased by about a metre, some are reduced by about half a metre, and of course it's much bigger when we get to say the 1 in 1,000-year event. Now, the reason for that is this isn't to do with data errors. This is mainly to do with a combination of modelling and the lack of data. And one of the issues which we haven't taken into account when we do the extreme predictions, we tend to deal with recorded data, digitally available data, national tire gauge networks. We don't tend to look at other data. So, for example, the Silloth tire gauge is in the Solway Firth. Data has been available off the Silloth tire gauge since 1987, and if you just taken a few months of the data from the tire gauge in 1987, you would have been able to sort of appreciate that the predictions that in 2011 were a little low, put it that way. So I would suggest that how things like change in the future. These are how things have changed between 2011 and 2018. How are they like to change? Your predictions in 2025, you may find predictions that some place, particularly in Scotland, may increase by not just a few millimetres due to data errors. They could increase by tens of centimetres. I don't know, I'm just suggesting. I'm just suggesting you need to be aware that extreme predictions due to data errors may change a little bit, but due to sort of models or other available data, they may be changed by quite a bit. Okay, any questions?
Thanks, Dominic. And I think it's just in the chat. If you have got any questions, do pop them in the Q&A button below. If I'll give it 2 or 3 minutes just for people to think of any questions. If not, I might have a couple, Dominic. So,
okay.
But if not, I'll give it a couple of minutes, and then if anyone's got any questions, just stick them in the Q&A, and I'll read them out. I think we have a good question from Amanda here, Dominic. I'll read it out to you. Fascinating talk, thanks. Why is the state of our tire gauge data so poor? It must be very frustrating for people working in this field.
Well, the UK tire gauge network I would suggest is possibly the best in the world. I think there's several reasons. There is a tendency to put a tire gauge in for a reason, and you only ports only want to look at tire gauge data for specific reasons. They put the tire gauge in. They may want to look at it on a specific day, and most of the time they don't want to use it. However, I talked to somebody from the EA about this, about the EA tire gauges, and one of the reasons they gave was that if, say, for example, you have I don't know, things like fishing rights, and you're allowed to fish, say, at a certain state of the tide, if you set those up and then you go back a few years later and you realise, actually, you know, we're going to correct our tire gauge, and then the fishermen find out actually they can't fish when they used to anymore because they've changed the datum. It's politically, it's not a good. It's not a good idea. So I think a lot of it is political, as in the tire gauges are set up for a reason. They set levels for, say, fishermen or whatever, and it gets very, very difficult to change them. Funding, there's also a lack of funding. I think there's also a bit of a lack of drive as well. The national tire gauge network is actually, despite what I've said, is actually a very good tire gauge. It's a very good standard. But I think there's probably been a lack of understanding of datum errors over the years. I think there's the Immingham. I mean, the Immingham and tire gauge. I mean, I said I'm only aware of 2 tire gauges we have a thorough review of the datum shifts, and I wouldn't be surprised if many of us have the same issues. but they're also very difficult to detect. It's incredibly difficult to detect a datum shift, and it's even more difficult to detect a historic datum shift where you don't, it's very easy to detect a current one, you just go back and re-level the gauge, but historically it's very, very difficult. But certainly I think we need more effort, for want of a better phrase, more money spent on looking at the quality of the Tyre gauges, particularly when we rely on them very often for things like climate change studies, etc. Okay.
Thanks, Dominic. It's a really comprehensive answer. There's a few questions coming in now, which is great. So Bryony, she's asked, if you were to put a factor of safety on the extreme level predictions, what value or percentage would you choose?
Well, it's not a percentage because no concept of percentage really in sea levels. If it's low return periods, I think we've got a very good handle on low return periods. You can just do a simple count back of sea levels to get them. So you can say, if you've got 30 years of records, you won in 1 year levels about the 30th highest value. In terms of low levels, that's fine. In terms of problems with the datum, all right, I said you had about 150 mil datum shift on the England Tyre gauge on the 2013, but that had only been over a relatively short period of time, and that may have been picked up later on. So, but I would suggest that datum shifts, for example, are probably not undetected datum shifts, are probably less than about 10 centimeters. So on low return period events, you can say that you're within 10 centimeters what it truly is. On high return period events, it'll be the 10 centimeters plus what level of confidence you have in the extremes. 100-year level, maybe 100, 200 mil, possibly, but I wouldn't say there's a right answer for that. But certainly on datum shifts, I would say 100 mil, 10 centimeters is about the most you need. But on actually the level extreme predictions, that's a completely different question. But it could be 100, 200 mil, but for the 100-year level, but I wouldn't want to be quoted on that. Okay.
Thanks, Dominic. Another question from Amanda. How confident can we be in the EA's guidance for coastal predictions for the future use in planning our risk assessments, given the data issues? I work for Yorkshire Water, very interested in future sea level rise.
I think, despite what I've said, I think the coastal flood boundaries, I think are fairly robust. I think there's potential problems where we have lack of. I think the prediction in Scotland could change quite a bit. They fixed the issue. I think they've got the issue right in Cumbria. There may be places around the UK I'm not aware of. I don't know, but I think the predictions have increased significantly since 2011 to 2018. I think they are looking at other sources of data for the next coastal flood boundaries. If you work for Yorkshire, I mean, there's been a number of issues on the Humber over the years. I think those should all be mainly sorted. They should mainly be sorted out now. But yeah, I think, despite what I said, I think the only potential surprises are probably in Scotland. I think we could find that there could be some surprise in Scotland how extremes change, but then because of the nature of Scotland with all these islands, the sea levels don't change very much anyway. So if we do get them wrong, it probably won't be significant because extreme aren't particularly high there anyway. But yeah, so I think Scotland could be an issue. The rest of the UK, I think, is probably okay now. They've changed. There's been a marked improvement since 2011 to 2018, and I don't think we're going to have any major surprises on the next coastal flood boundaries, although I could be wrong.
Thanks, Dominic. A question from Steve McFarland. For a new installation, what types of instruments are more likely to give reliable results?
I don't know, not my field. However, I would not suggest radar or acoustic ones because unless they're in a tube of some description, for the simple reason you can get rubbish, animals getting in the way. There is a tendency to move towards them. Pressure ones, pressure gauges do seem to work very well, but I'm not really the person to ask about that. But I mean, the issue I mentioned at Workington, I've never seen that before. and I only picked that up by accident. I'm not aware that that's has been an issue anywhere else. But I don't know. I'm not my field, but I would imagine that pressure devices are very reliable and accurate, or probably most reliable and accurate. Although we may be moving towards acoustic or radar ones because they're cheaper. I believe they're cheaper. Okay.
Okay. John Powell, who we know. Thanks for this, Dominic. We see lots of effort in understanding extreme high waters. Are you aware of any similar investigations on extreme lows?
Hi, John. I know where this is coming from. No. I'm not aware that, apart from, I'm not aware that we do very much on extreme. Well, I've done extreme low level analysis. One of the problems with extreme low level analysis is that the conditions that give very low tides are the opposite to what gives very high tides. If that makes sense. No, I'm not aware of anything really being done on low waters, or very little work. I mean, the only place I think they want them is for nuclear power stations for cooling the water intakes. But there's I'm not really aware of anything beyond that, or any studies or anything. I think I answered the question, John. I may have misinterpreted what you thought. Okay.
Thanks, Dominic. Colin Smith, a question here. The contrast in Orkney and the Pentland Firth is eye-catching. Any thoughts of why there is both a significant increase and significant decrease between 2011 and 2018 in quite close proximity to each other here?
I don't know, but it will be lack of data, and I don't know, it may be something wrong with the model. I honestly don't know. Fundamentally, lack of data. I mean, there's quite a lot of tide gauges in Scotland. You get lots of things happening around Ireland, but I'm not a coastal modeler, so I don't know. But fundamentally, it will be lack of data. I do agree; it is quite surprising how the changes. But I don't know. It'll be probably the modelling isn't modelling could be better. I shouldn't really say that because people who do the modelling know an awful lot more about it than I do. But yeah, fundamentally lack of data. I can't miss any more.
Thanks, Dominic. There's no more open questions. Feel free to put them in. I've got a question here, actually, Dominic. So how common is this flatlining, whereby the gauge is not calibrated high enough to cover the largest events, such as the 21st? In that sense, I guess, with sea level rise, is that going to become more of a problem in the future as well?
I've never seen it on a national tide gauge network. I don't think I've seen it on EA tide gauges, although I could be talking rubbish. I may have seen it and not realised. It does occur on EA tide gauges, sorry. It depends on the organisation. It seems to be more common with ABP tide gauges, I think, from memory. Sometimes, actually, so no, it does sometimes occur on EA. It's not that common. But then again, it only ever occurs when you get a very large sea level, so therefore you wouldn't necessarily notice it. There is a tendency for, I think it gets missed as well. I think people miss it. I think tide gauge is flat line, and people don't realise because they just take the data. But yeah, I think on the Humber, I think I noticed it on about 4 or 5 tide gauges. So Sperm Point, I think there was one at Ferriby, it happened, and somewhere else, I can't remember. But I think it's probably more common with ABP tide gauges than EA tide gauges. I've never seen it on a national tide gauge network tide gauge.
Thanks for that.
Okay.
Thanks for that. All right. This question from Caroline. Is the modelling undertaken to Ordnance Datum Newlyn, and are most of the tide gauges levelled in Newlyn to Newlyn, or are there any data conversions in the study, such as to mean sea level?
Yeah, they're levelled to Newlyn. Although that's interesting because one thing to talk about is that mean sea level is not 0. So yeah, the tide gauge is levelled to Newlyn, and mean sea level changes all around the UK. So just a matter of interest, mean sea level down the south coast of England is about 0.3, and in Scotland it's about 0.2 generally. And the reason for this is because when mean sea level was set up in 1915, sea levels have obviously risen and Britain is tilting. So Scotland is rising, the south of England is sinking. So that's why mean sea level is slightly different. So they are set to Newlyn, but mean sea level is not the same everywhere anymore. It tends to be around about 0.2 in Scotland, around about 0.3 in southern England, generically.
Thanks, Dominic. There's no more questions that I can see here. I have a question I just thought of, but you say the UK Tide network is probably the best in the world. Are there any other lessons though that we can learn from other countries that also record Tide very well?
I don't know. I'm not as familiar with. I don't look at other Tide gauges at the same level as I look at in this country. I don't know, Sam. I'd be willing to learn, but I can't think there's anything elsewhere that I'm aware of. Anyway, they do talk to each other, obviously, you know. Yeah. So, but I'm not aware of anything that we could learn. I don't mean that as an arrogant statement. I just mean I can't think of anything that we can learn from other countries that we don't already do.
Right, no, that's fine, Dominic. If there's anyone on the call that might know anything about different countries' system, feel free to put it in the chat. It'd be quite interesting, I'm sure, for Dominic and myself and anyone else to know. We don't have any more open questions. I'll give it perhaps another minute, and if there's no other questions in, then we can end the webinar a little earlier. But I'll give you all attendees to just stick in any more questions as needed. I think we're not going to get any more questions, but so I'll end. If we end it now, that'd be. And thank you for all attending. If you see in the chat, if there's any links that Barbara has put in and the things I taught, feel free to copy and paste them over so you know where they all are, and do check out future SciWem and RCG events. Thank you very much to Dominic for preparing a really interesting talk. Anything more, I'm sure you can. I think you can email me. It should be on the SciWem event page, and I can forward to Dominic as needed as well. So
sorry for almost losing my voice. I've never lost my voice when talking before, so I had to drink a cold cup of tea to try and get my voice back.
It wasn't noticed, Dominic. It's okay. All right. Thank you, everyone, and have a good rest of the day.